So this is a 3 by 3 determinant. You can do, we've talked about this very recently, so I don't want to dwell on it too long. You can choose a value of x right now, right? And see if you'll get a non-zero answer. You only need to get a non-zero answer once. But, right, so if you find even one value of x that gives you a non-zero determinant, it's a linearly independent set, and you're able to stop. If you choose a value of x, though, and you get a Wronskian of 0, then you have to go back to the drawing board and maybe try another value of x. And it could end up taking a while. What do you guys think?
0 and 1.
I like to try, numbers that are low-cost numbers to plug in. I can plug in 0 easily. So let me just try 0. So I'm going to get 0, -1, 3, 1, 0, 0, and 0, 2, 0. Oh yeah, that's looking really good. That's going to have a Wronskian of 6. Just by the arrow method, you can see that it's 6. So you got a non-zero number, so yes, they are Li. Can anybody think, so I gave one reason, can anybody think of a second reason why the 3 polynomials over there are definitely Li?
You can put C1, C2, C3 in front of them, and then because it's x squared and x cubed, for that to equal 0, C1 and C2 and C3 must all equal 0.
So Curtis is reminding us of going back to the basics of the definition of linearly independent vectors. And that will work. Essentially what will happen is your vectors will end up in the columns of a matrix, and you'll row reduce that matrix, and you'll see that there are no unpivoted columns. And that just means that there are no free variables, so there are no linear dependencies. Let me give you, and that will work. So you could say, use the definition of linear independence. Let me just give you one more really quick that's easy to see. The first 2 vectors, just the first 2, are linearly independent because they are not multiples of each other. Just the first 2, right? So the first 2 are definitely linearly independent. Now this third one involves x cubed, which the first 2 do not have in them. So these first 2, as you can take linear combinations of these first 2 vectors until you're blue in the face. You can do it forever. Take all possible linear combinations. You will never be able to reach that third vector, which means that the third vector is outside of the span of the first 2. Well, if you bring in a vector that's outside of the span of the first 2, then you are safely avoiding a linear dependency when you do that. You're not going to make a linear dependency because you're bringing in a vector that's not expressible in terms of the 2 that you already have. Okay, so that's another way to think about it. So I'll just say third vector is outside the span of the first 2, which was x and -1 plus x squared. So that's another way you could explain it. Doug, you had your hand up a little bit ago.
My question, if you could just say basically by looking at it that it's obvious.
Yeah. In this case, it is fairly obvious. Yeah, one.
I'm sorry, but I'm not seeing how you got the basics from what equation to feel it.
I really went to this one up here, which I know has a lot of stuff around it already. Yeah, basically I busted out, there are 3 variables up here, which are the b, the c, and the d. So I busted those 3 out one by one, and each time it gave me a polynomial. So I have 3 polynomials. Does it seem reasonable?
Yeah.
Okay. Okay, great. Everybody all right with those 2 examples? Okay, super. Let's go on. Let's talk about linear transformations a little bit. Yeah, Ken?
Actually, for the basis,
Yeah.
how many points would you take off if you accidentally put in coordinates column instead of like?
Oh, if you didn't write them as polynomials. Oh, yeah, that's a good question. That's a pet peeve of mine. My answers should be polynomials if my vector space is polynomials. So I don't know. It would probably be no more than half the credit, but it would be sizable. You don't want to make that mistake. Be sure that you're writing your answers in a form that at least it makes sense, right?
Talking about tuples, right?
Right. So right, I don't want to see x written as 0, 1, 0, 0, and then -1 plus x squared written like that, and 3 plus x cubed written like that.
You can only write that when you give it equals?
Right, exactly. If this was a problem about vectors in R4, then of course this would be fine. And this would be what I would want. But if we're talking about a vector space of polynomials, my answers should be polynomials. This comes under the heading of, you know, at the end of the exam, you've finished everything and you're going back and checking your work. This is the sort of thing that you would catch. You would say, wait a minute, let's reread the question again. The question was about polynomials, and I gave an answer that was a bunch of tuples of numbers. That's not the right kind of answer. So, although the calculations are all correct, and you pretty much have the answer, it needs to be expressed in the right form. Okay, so that's a great point, Kevin. Thank you. Okay, any other questions about that one so far? Okay, let's move on and talk about linear transformations a little bit. We haven't done linear transformations since before spring break. We did it around the time when we switched our clocks forward. So that's been a while. So let's do problem number 5 on the sheet here. So number 5, doing a lot of linear algebra here to start off with tonight, which I think is fine because we've been doing so much differential equations lately. So here you go. We're going to define t to go from m2 of r to r squared via t of, I take a 2 by 2 matrix, so I'm going to call it A, B, C, D. And we're going to output 2 numbers. The first entry is A minus B minus 3C, comma. Second entry is 2B plus D. And we're going to ask several questions here. The first question is going to be, show that t is linear. Okay. Can somebody remind me, showing that a transformation is linear involves what? Great. 2 parts, right? Just like subspace. T has to respect addition and scalar multiplication, and hopefully everybody knows kind of what that means. Respecting addition just means that if I take 2 inputs and I add them together and then transform them, I need to get the same answer as if I transform them separately and then add the results. So the way I like to do this is I like to start out by just saying T of, take 2 by 2 matrices, A, B, C, D, and then maybe I'll call the second one A1, B1, C1, D1. Okay? And you group them together like that. So you add them inside the parentheses. The T is kind of on the outside of the whole thing. Does this look familiar? Right? The respecting addition, the generic way it would look is T of V1 plus V2 equals T of V1 plus T of V2. So that's the generic way of expressing it. So that's what I'm doing here. Here's V1 and V2. Okay? So what's the first thing we need to do here? Add them on the inside, right? You have to add them first before you can transform them. See, T, if you look at T, it only knows how to handle 1 matrix at a time. And I don't have 1 matrix here, I have 2 matrices. So I need to combine them, I need to add them first. So if I do that, I've got T of A plus A1, B plus B1, C plus C1, and D plus D1. So I first want to combine them like that. And now I'm ready to transform this thing. So how does that work? Well, just follow the rule here. Upper left corner minus upper right corner minus 3 times lower left corner. So that's going to be upper left corner A plus A1 minus upper right corner, so that's minus B minus B1. And then minus 3 times the lower left corner, that's minus 3C minus 3C1. Comma. second slot is 2 times the upper right corner, so that's 2b plus 2b1, and then plus the lower right corner, which in this case at this point is d plus d1. Okay? So far, is everybody with me? Now, sometimes people get a little lost in the middle. It's like, okay, what do I do next? If you see it, if you know what to do next, that's fine. If for some reason you're having a little trouble seeing, well, what do I want to do with this thing? That's all right, don't panic. What you can do is look at where you're trying to get to. You're trying to get the transformation of the first vector separated from the transformation of the second vector. So the transformation of the first vector should just be this, right? As printed. And the transformation of the second vector should be this with subscript 1s on everything. Right? So what does that tell you about what you really want to do with this?
Separate them.
Separate it into how do you want to separate it?
To the one percent.
Into 2 different things, right? And how do I know what stuff was going to go with what part? Yeah, basically the terms that don't have the subscript 1 need to be put together, and then the terms that do have the subscript need to be put together. So I'm going to have a minus b minus 3c, comma 2b plus d, and then in the second slot I've got a1 minus b1 minus 3c1, and then in the second slot 2b1 plus d1. I think I did that right. And that is actually what we wanted to get, because the first thing is T of the matrix A, B, C, D, and the second term is the matrix A1, B1, C1, D1. So you're just going to write all that down. Does that make sense? So that is showing that T respects addition. Takes a little bit of writing, but we can get through it pretty well. Okay, what else do we need to check? Jake?
Real quick, does it matter which way we go?
Oh, no it doesn't. Although I will say this, I typically find that people do better if they do it in the order that I've shown it here. In other words, it's better, I think people do better by starting from T of V1 plus V2 and ending with T of V1 plus T of V2. Generally, people do better when they do it that way. Okay? But yeah, there is this one step in the middle where you have to realize how to split it apart into 2 terms. That's really the key step, actually. You know, there's no hard and fast rule about how many steps you can skip before it, no longer like clear what work you're doing. Sometimes maybe not every step needs to be shown, but obviously I don't want to see somebody jumping from like here all the way to the end. Okay? You shouldn't do that. You'll have plenty of time to write out a little bit more. I mean, you're really trying to convince me that you know the material. If you write down all the steps in the middle, I couldn't be more convinced. Otherwise, you're going to make me guess, gee, I wonder if they really knew what they were doing or just jumped to the end. And I don't want to be in that position. So it's much better to just write it down. Overwrite it than underwrite it is better. Okay. Scalar multiplication, should we check that real quick? Okay, so T respects scalar multiplication. Okay, so we need to grab a scalar. Let's call K a scalar again. Let K be an element of the real numbers. So then we're going to take T of K times A, B, C, D. What do I do first here?
Distribute the K across.
Right, multiply through by K everywhere. So it'll be KA, KB, KC, KD. Alright, and if I want to transform that, I have a formula for it. So it's going to give me 2 slots, which are going to be, the first slot is going to be upper left corner minus upper right corner minus 3 times lower left corner. And then the second slot is going to be 2 times the upper right corner plus the lower right corner. And what are you just staring at you here, are you dying to do right now? k can come out, right? There's a k in every single term, right? So you want the k on the outside. Let me just remind you guys, basically, we're trying to show that t of k times v is k times t of v. We want that k to get pulled on the outside, but it starts out on the inside. This is another example, guys, where I see people starting on this side. They start with the k on the outside. They, somewhere in the middle, they put it on the inside for a second, and then the very next step they pull it right back out again, and they start and end right here, and they just do a circle, and that's really not proving that it respects scalar multiplication. So let's be real clear here. I started with the k inside the transformation, right? But now it's going to come all the way out. So we pull it out. It'll look like that. And now this is just k times t of a, b, c, d. Yeah, Sergio?
Should there be a T in front of all those, like the middle steps?
Oh, good question. What do you guys think? You know which steps have the t in front of them? The steps that have the t in front of them are when there's a matrix there.
Oh,
As soon as I have a pair, an ordered pair, it means I'm on the output side of the transformation. I'm in R squared at that point. Oh, and actually, if you were to put t's in front of either of these steps, that comes under the heading of doesn't make sense. Because now you're trying to transform a vector in R2, but this transformation does not take vectors from R2 as inputs. They are the outputs. And so I don't want you guys to confuse inputs with outputs. That's like a major confusion. It's very hard to understand what you're doing at that point. Sergio?
So when we use the rule or when we use the transformation, that's when we take the T away.
Right. Where does the t actually disappear? It disappears the second that you use the t to do something. It's like when you integrate x squared dx, right? You come over to the other side of the equation. Do you put an integral sign in front of this?
No.
No, you just did the integral, so the integral sign vanishes at that step. It's the same way here. You just did the transformation, so on this line, there is no capital T in front of that step. Good point. Okay, is everybody comfortable with this? So this thing is linear. This thing is linear. Okay. What I want to do next, this is actually, I thought I had caught all of these little glitches. I was, you know how I kind of finished the semester, I was ahead of schedule and everything, and I, had plenty of time to kind of get done with the last few sections. It wasn't like that all semester long. So before spring break, I was actually behind schedule and stressing out, and I didn't really cover section 5.4 in the full depth that I have sometimes in the past. In particular, I don't think I ever talked about what one-to-one means. Does anybody know what one-to-one or Everybody's freaking out. I think on the review packet for the second test, I wrote something like ignore for now or something. Yeah, I should have said ignore forever. Well, I thought I might come back to it, but I never did. So as far as that goes, when you see questions about one-to-one, onto, both, or neither, and there might be one on the sample test as well, you don't need to worry about that. So actually, there's little trade-offs that are like I think the last time I taught the class, I did go over one-to-one and onto, but I didn't get to the stuff about W3, W4, and W5. So there's hit and miss on these different things. I have to you want to trade? Yeah. We could just do it all. No, I'm just kidding. Let's not worry about actually, I don't feel badly about it because one-to-one is a very simple thing. It just means that the kernel is trivial, and onto just means that the range is the whole space W. But I'm not going to bother you about those words. I'm just going to ask you, what is the kernel of T? What is its dimension? So on and so forth. So let's move on to part C of this. So part B, we're going to ignore. And I want to go on to part C and talk about a basis. So let's find a basis for the kernel of T. Find a basis for the kernel of T. Okay, does anybody know how to do that?
set the second part equal to true.
Right. Basically, the kernel of T is which inputs get sent to 0. So basically, let me just remind you that kernel of T is the set of vectors V in capital V such that T of capital V is equal to 0. It's those vectors that get killed by capital T. So in this context, it would be T of A, B, C, D being sent to the 0 vector, which is just 0, 0, which means that A minus B minus 3C, comma, 2B plus D, that has to be 0 and 0. So we get these two equations. Okay? Yeah, kind of. So the kernel is, yeah, it can be. I mean, it's going to end up in a matrix eventually, but I don't want to jump that quickly through it. Basically, the key thing here is that the kernel is a subspace of V. So my answers should look like what kind of creatures? 2 by 2 matrices, right? Please, folks, keep your V and your W clearly in mind. This is so important because when I'm talking about the kernel, I'm talking about vectors in V. And when I'm talking about the range, which we're going to do in a minute, I'm talking about vectors that are in W. So the V and the W are playing a key role here. Okay? So that's what we're going to do. We basically want to solve which matrices satisfy this. But this is just a system of equations. It's just a system of equations, right? So we have A minus B minus 3C. That has to equal 0. And then 2B plus D. That has to equal 0. If I want to solve that system, what am I going to want to do? Right, build a matrix for it. So we'll build a matrix 1, -1, -3, 0, augmented with 0. And then 0, 2, 0, 1, 0. And my variables are just A, B, C, and D. I'm obligated to row reduce that. It already pretty much is in the right form. The key thing is always, where are the pivots? That's when I'm solving systems of equations, the key to everything is where are the pivots. Remember, every system has either 0 solutions, 1 solution, or infinitely many. And the way you decide which of those 3 scenarios is right is by looking at where your pivots are. What you can see right now is how many solutions do you have here? Infinitely many. You have 2 free variables, don't you? D is free, I'll call it T. C is free, I'll call it R. B is not free, but I can solve for it in terms of D using the second equation. So the second equation is -D over 2, but that's really -T over 2. And then the A equation, A is not free either. A is solvable from the top line. It's just literally B plus 3C, right? So B plus 3C, that's going to be -T over 2 plus 3R. Okay?
Would it be positive?
Yeah, what are we positive?
It's B plus 3C. So it's actually -T over 2 because... Okay. Okay, so how do you guys feel about this for the basis for the kernel? Basis for the kernel, I'm going to bust out the T. I'm going to bust out the T, and then I'm going to bust out the R. Basis for the kernel? I need to put my braces around here. Is that a basis for the kernel?
I want to see.
The trick question. What's wrong with that being a basis for the kernel? Jake?
It would be a 2 by 2 matrix.
Exactly. These are not 2 by 2 matrices. Remember, what are your kernel vectors going to look like? They have to be 2 by 2 matrices. Not column. These look like vectors in R4. I don't have R4 anywhere in this problem, right? So I don't want to write it like this. I'm not saying you would get 0 points for putting this down, but you would lose something substantial because you're not giving it to me in the right format. So the basis here, the basis should be, so if I do it in the form of A, B, C, and D now, if I bust out the, let's see, basically it's just these vectors, but put them into a 2x2 matrix instead of a column. So it would be -1/2, -1/2, 0, and 1. Excuse me, and then comma 3, 0, 1, 0. It's going to look like that. So that's my basis. Is everybody comfortable with that? Okay.
Wait, Professor?
Yes.
So you said when we're doing the curve T, it's always the first or before we transform it?
Well, your kernel is a subspace of V.
Okay.
Yeah.
So it's okay.
So whatever the vectors in V look like
That's
is what your vectors should look like
Okay.
for the kernel. Okay. Everybody good with that? Okay, question. Does anybody know about what they can tell me about the range of T on this problem?
It's an R2. So it's
Actually, can anybody, sort of gold star opportunity here, can anybody tell me what the range of T is right now?
so a matrix of 1, 0, and 0, 0, 1, which is an R2.
Okay,
It's not a matrix, it's just the coordinates, like 1, 0, 0, 1.
so 1, 0, and 0, 1, that is the range of T?
No, they're separate.
Like together in that's a basis.
A basis for them. Yes, okay, good, that's what I wanted to hear. A basis for the range of T would actually be 1, 0, and 0, 1. Why do you know that?
Because the range of T is everything that comes out of the transformation. So
Okay.
everything that comes out of the transformation is like all of R2.
How do you know that all of R2 is going to come out of that transformation?
They're like, it's just, you can just, like,
You can just kind of tell.
yeah, you can just kind of tell
Okay.
how to say it.
I know what you mean. Basically, okay, I kind of know
No
what
way
you
that
mean.
it won't.
Let me tell you another way that you know that that's the right answer. Guys, if there's another part of this, which is what is the range of T? The answer, and we should all know this answer, we should actually be able to arrive at this answer with no work at this point, which is, it is all of R2. Generally, the range of T is a subspace of W. Right? In fact, I don't know if how well you guys remember this. The range of T is a subspace of W. Specifically, what subspace is it? This maybe should be on that list of formulas that I gave you at the beginning. The range of T is the span. So if it's the span of something, then it's a subspace. Okay. And what is in this list? We have to go back to the material from chapter 5. T of V1, T of V2, plus T of Vn. So the V's, V1, V2, up to Vn, that is a basis for V. So you take a basis for V, and of course here we have a 4-dimensional space, so you would have 4 vectors. You would transform all of them, and you would write the word span in front of that. And it would be a subspace of W. Okay?
Would you repeat yourself one more time? What you said?
What I just said is that to find the range of T, you need to just calculate it directly. You take a basis for V,